Hello, everyone. Welcome to the first lecture. Now, we already started section 7.8 about double integrals. So today we're going to quickly review 7.8 and then finish with 7.9. So note that this is a video that I expect the students to be watched before class. Therefore, some details will not be covered. Instead, we're going to finish them in class. And you can also try to fill the gaps while you watch the video. I encourage you to take notes. If necessary, pause the video. And it's normal if you have questions. And we will discuss your questions. You can also post them at the forum or ask me if we do not have time in class. Also, this note itself, which I'm going to write, can be downloaded. Okay, so go to our course website. You can download so that your note taking will be easier. Okay, so let's go to the next slide. So first, let's review our definition of indefinite integral. It is the family of antiderivatives of a function. That's what we call ordinary integral. Now, suppose we have a function of two variables, f of xy. The integral with respect to x, because x is only one of the variables, so we call it partial integral. And it is a partial antiderivative, big F. Okay. With the partial derivative is the integrand e to f plus a constant. This constant here is a constant with respect to x. So it can still be dependent on y. So we denote by c of y. Okay. Similarly, the partial integral of f, little f, to y is a function g whose partial derivative to y is little f, and plus a constant c of x, okay, which may depend on x, but independent of y. Okay, let's see an example. This example is actually from our slides, and the file of our slide is also posted. And the first question is to integrate 2xy to x. Okay, so let's do it here. Integral of 2xy dx. Since we integrate to x, so y is a constant. Therefore, we can pull out 2 and y, okay, which is a constant factor, out of the integral. Look at this. Now we know well by the power formula, antiderivative of x is x squared over 2 plus a constant with respect to x. And it could be a function y, so we write it as c of y. Now, that's our answer. Let's simplify this. Get 2 canceled, get y x squared plus c y. And that's our answer. Now we can easily verify why this is true, by just by checking the derivative of this function. Okay, this is partial derivative of this function 2x. And they take the derivative of the first term, we get y times 2x plus the derivative of this term, which is independent of x, so the derivative is 0. And that is 2xy. And this is the same as the integrand. Okay, so we can verify this. And this example also shows that when we integrate it to x, we just treat y as a constant. Okay, that's the first part. The second part, we needed to integrate this same function to x, but from x equal to 1 and x equal to 2y. So that's worked here. So integral from 1 to 2y to xy dx. This is a definite integral. We still have the well-known fundamental theorem of calculus, which is here. Okay, so here the big F is any partial antiderivative of of the integrand, and this is the fundamental theorem of calculus. So in this case, we already found a antiderivative of this, which is y x squared, and evaluate at x equal to 2y and x equal to 1. We write this here as x equal to 1 just to make it clear that those limits 1 and 2y are for x. So notice here, yx squared comes from here. The antiderivative we found earlier. We do not have to worry about the c of y because it does not affect the integral here, the definite integral. So now let's finish this. We evaluate this function at actually y times 2y squared minus y times 1 squared. Just evaluate this function at x equal to 2y and x equal to 1. And we can simplify this to get 2y squared, to get 4y squared, 4y cubed minus y. So that will be the second integral. Okay, so let's continue here. We're going to look at another example. Okay, in this case, the first integral is a definite integral of 2xy plus 3 with respect to y. For y, start from 0 to x. Now, this is similar to the previous example, 1b. So I will not go to detail here. Basically, we needed to find, start from here. We need to find the antiderivative of the integrand with respect to y and evaluate at y equal to x and y equal to 0. And this will be the answer. You can work out the details if you are not sure. Okay, now let's look at the second integral here. Actually, the second part, the problem is here. Okay, it's to find the to find this integral. Notice that here this is a kind of iterated integral, or some people call it double integral. Okay, and the inside here, there are two integrals here. The inside one is the same as the one we just worked out. Right? You see that? The inside one here. Okay. And then we are going to integrate the resulting integral. Okay, so here, let's work this out here. The integral, let's copy this one from 1 to 2. And the integral we just worked out, let's copy it here. Integral of 2xy plus 3 dy dx. So this is already worked out. So just replace the inside integral by x cubed plus 3x dx, right? So now we get integral in calculus 1. Okay, so we find the antiderivative. It's 1/4. Yeah, 1/4 x to 4 plus 3/2 x squared. And evaluate at x equal to 2 and x equal to 1. Okay. So when x equal to 2, get 1/4 times 2 to 4 plus 3/2, 2 squared, right? And then when x equal to 1, I get 1/4 plus 3/2. Okay. So this one here, we get a 16, and with 4, I get a 4. And here 4, we get 3 times 2 minus here. Here we can, combine the two terms. And so you get a 1 plus 6, 7 here, right? And 10 minus 7/4. And we get 33/4, like that. So that will be the answer of this definite integral. So here we see we have worked out double integral here, and this double integral actually the official term of this integral is called iterated integral because it's kind of layered integrals. Okay? And this kind of layered integrals are what we used in the text to define a so-called double integral. And we will do that in the next slide. Okay, so now we're going to define a double integral of this form. Okay, it's called a double integral because the function has two variables, x and y. Okay, we're going to integrate this function to x and y. Now the order here is dA here could be dx dy or dy dx. They are really the same, but when the orders are different, it indicates that we are going to integrate one first and another one second. The variable we integrate second is also called outer variable. Like in this case, this would be y is outer variable if we write it this way. And here x is the outer variable. And R here is the domain of a function. The domain of a function, or is part of the domain of the function. Okay, so we're going to consider two cases. The first case that, the R here is defined by the following inequalities. Okay, so let's see first one. So R is a region in the plane. Okay, the points in R has coordinates x and y, and x is between A and B. So x is here, x is between A and B. But for each x, let's see, suppose here's x, that's between A and B. Y is between the value of the two functions. Okay, so this condition really defines this vertical segment. It's called a cross section. Okay, that's for every x. So it's defined a region that can be said to be between two curves. One is from above, another one is from below. Okay. This type of region is also called type 1 region. Okay. Now suppose our R is type 1 region, and we're going to define the double integral here. Okay. Integral of f on the region R, okay, with respect to x or y and x. Now in this case, we are going to integrate to y first. Okay. Now notice that for y, it is between the values of the two functions g1, g2. Okay, that's the first integral, or the inner integral. And the result of this inner integral is a function of x. And then we integrate this one with respect to x, this function, from x equal to a to x equal to b. So that's how we define this double integral. Okay. It is not the original definition, but for our purposes, we use this iterated integral as a way to define this double integral. Okay. So in this case, dA here, is written as dy times dx because it is because y is integrated first. Now notice that what happens if f equal to 1. If f equal to 1, that means this equal to 1 here, equal to 1. Then when you integrate to y, okay, from G1 to G2, we just get the length of this interval. So in this case, if this is 1, okay, then we look at this integral here with f equal to 1. The first integral inside becomes this. This is the result of the first integral. And now we integrate the difference of those two functions. We get the area of R. That's what we learned in calculus 1. Okay. So when the integrand is 1, the double integral is just the area of the integral domain R. Okay. And this is the case when the region is so-called case 1 or type 1. Okay. Now there's a type 2 case, and so that's the next slide, and it's kind of similar. Okay, notice, so let's point out the difference. Okay, in this case, again, the region R is defined by the condition for the coordinates of a point. Okay. And so here, y here is between C and D. Okay, that's the first condition here. Now for every y here, so suppose this is a y here, this is a y here between C and D, the cross section here is defined by this. Okay. So in this case, we're going to integrate, with respect to x first. Okay. For each fixed y, we integrate to x from here to here. Yeah. And then we get the result is going to be a function of y. So here we integrate to x first, okay, from h1 of y to h2 of y. Okay, so this integral here is the integral on this interval, this cross section, and then we integrate with respect to y from C to D. Okay. So we get another definition. Now, sometimes it's possible that the region R can be defined as a type 1 and a type 2 region. In that case, the two integrals or the two definitions will give us the same value. And similarly, when the integrand is f, okay, now notice in this case we already have replace this integrand by f, then this integral is the area of the region. Okay, so here let's look at the example, which is also from our slides. And in this example, we have a iterated integral. And we needed to sketch the region R on which the integral is defined. So let's see how is this R described. From this integral here, it's easy to see that here we have y is between 0 and 2. Notice that here, y is the outer variable, and its limits are 0 and 2. X is between y squared and 4. So what is the region? How is this defined? What does this region look like? Well, we can look at the region here. Y is here between 0 and 2. Okay, so let's plot this one. Okay, so here's 1, 2, so y is here. So we have to look at this one here, this condition. Now here, the second condition, we have y squared equal to x, which is the same as y equal to root of x. Yeah, because y here is positive, so y has to be root of x, not negative root of x. And we can plot this graph. Okay, that's y equal to root of x, which is the same as x equal to y squared. That's one side of the region. The other one is x equal to 4. So we consider the equations defined by the equality here and the equality here. And x equal to 4 is is 1, 2, 3, 4. Look at this. Okay, it's x equal to 4. It's a vertical line here. Now this should match here. Okay, this should intersect here. So now we can see what is the region bounded by the 4 conditions. Y is between 0 and 2. X is between, y squared, which is same as this one, and x to the 4. So we see this is the region we are talking about. So this region is, described as now. It is actually. Let me pause this for a moment. Okay, now we can look at the second question, which is to rewrite the integral so that x is the outer variable. Now, which means we're going to change the way of R is described. So based on this graph here, R can also be described as follows. X is between 0 and 4. Y is between, so X is between 0 and 4. And Y is between Y equal to 0. And then Y equal to root of X. Okay. Y equal to root of X here. So the same integral from 0 to 2, from y squared to 4, and dx dy defines our double integral over R of dx dy. Okay, the integral here is 1. That's what we're given. Now, using this description here, okay, which is the so-called type 1 region, you can also write this as dy dx, just change the order of integration. For y, it's between 0 and root of x. And for x is from 0 to 4. Okay, so here we have to change the order of the integral. Now part 3 here is to show that both orders of integration yield the same value. And now to save time, I have done the calculation here, and they indeed give us the same value, 16/3. And I like students to work this out if you're not so sure. Okay, so let's, we have a couple more minutes. So we're going to look at some more applications of double integral. The first application is the area of a region, which we already talked about. And as a more general application, we can interpret this integral of a function f as the volume of the solid between the graph of the integrand z equal to f of xy and the domain R. Okay? If the if the function is non-negative, which means the graph is above xy plane. So we're going to look at problem number 6 in our online assignment. And the problem here is to determine the volume, the volume of this solid. Okay, that's under the graph of x squared plus z squared to 1, and above the this domain R. Okay, that's this triangle here, this triangular domain here in xy plane. So here, the notice that this R here, this is the domain or the bottom of this solid is described by this. X is between 0 and 1. So X is here, it's between 0 and 1. And the Y here, Y is between, Y equal to 0 and Y equal to X. Okay. So that's our R. It's really a, triangle. It's a right triangle. And with sides 1, 1, and this set is root of 2. Okay. Now to fit the formula, we're going to rewrite the equation of this surface above as the graph of a function. So we're going to solve for z from this. And what we get is z equal to root of 1 minus x squared. So that's our function f. This is our function f. And we integrate this function over the region R and represent it as a iterated integral. So this will represent the volume that we are looking for. Now let's finish this integral. Okay, so let's so we have v equal to integral from 0 to 1, integral from 0 to x, root of 1 minus x squared, dy dx. Now notice that to evaluate this integral here, it's a constant with respect to y. So the first integral will be just root of 1 minus x squared times y. This is antiderivative at y equal to x and y equal to 0. Okay, and then dx. So next step, we have integral from 0 to 1 and 1 minus x squared, taking square root, and x here, dx. So now we need to evaluate this. Okay, notice that here, this is a composite function. This is a composite function. And notice that the derivative of y minus x squared is a negative 2x, which is proportional to this. So we can let u equal to y minus x squared as a change of variable, and then let's calculate du, which is negative 2x dx. Yeah. And notice that x dx here appears here. So we can solve for x dx. We can also change the limits. Okay. So when x equal to 1, we get u. When x equal to 0, we get u equal to 1. When x equal to 1, we get u equal to 0. So the limits are changing. And this part goes to this, and this part here goes to negative 1/2 du. Okay. Because of this. Okay, so now here you can finish this one. I will give you as an exercise. You are going to get negative 1/2 u to 3/2 as an antiderivative, valued at 0 and 1. Eventually, you're going to get a 1/3. That's the area, that's the volume of this solid here. This solid here. Okay. Okay, as our last application here, we're going to define the average of a function on a region R. Okay. And so if we divide the integral by the area of the region, because this actually is A here. This is A. This A is for the area of the region R. Okay. It's similar to this. If you have a function f of x, if you integrate from A to B, okay, and divide by the length of interval, you get the average value of the function f. Okay. So this is the average of a function on a region is a generalization of the average of a function on an interval. So here, for example, if we consider the function in the previous example, okay, root of y minus x squared as a function of x and y, even though y does not appear here, okay, we can still ask what is the average value of this function, on the region R, which is the, that triangle. Well, we already calculate what we need. Okay. We needed to evaluate this integral, which is 1/3. And we need to divide by the area of this R. Well, R here is a right triangle with 2 legs, 1/2. So this becomes the area. So using the formula for the average value, we get this. We get 1 over 0.5 times 1/3. 1/3 here is the integral, and the answer is 3/2. Okay, so we will stop here. I know this video is a little longer than expected, but fortunately you can, watch at your pace, and you can skip certain part that you already understand well. So I will stop here and see you next time.